In section 8.1, we're going to be looking at angle measures in polygons. And discovery, first, is we're going to actually discover a formula for the sum of the measures of the interior angles of any polygon. We're looking for the sum of the measures, meaning the total of all of the angle measures in polygons. And what I'm going to do is start with polygon that we know, the first polygon, the least number of sides that you can draw, and that's a triangle. And you already know polygon with 3 sides is called a triangle, and this will make more sense in a minute, but the number of triangles in a triangle is 1. And you already know, because we've talked about this all year, what is the sum of the interior angle measures in a triangle? Well, you know the angles in a triangle add up to 180 degrees. That's something we already know. Good place to start. What is a 4-sided polygon called? That's a quadrilateral, and there's a lot of types of quadrilaterals, but we're looking at any 4-sided. And now what I'm going to do is draw a quadrilateral, a 4-sided figure here. And if you notice here, I said draw all the diagonals from one vertex in each. So if I just pick this vertex and I look for any diagonals I can draw, actually this is the only diagonal that I can even draw in this triangle from this, or in this quadrilateral from this vertex. Now the cool thing is that we now split into triangles. There is one triangle here, another triangle here. So there are 2 triangles in this quadrilateral, and then I should be able to find the sum of the interior angles, because if you think about it, you know this triangle, the angle measures would add up to 180. And you know the same thing here. The angles in this triangle should add up to 180. Well, together, these 2 form the original angle of the quadrilateral. This is an original angle of the quadrilateral. This is an original angle. And together, these 2 form that last angle of the quadrilateral. So really, I just have 2 triangles. And so you're thinking 2 triangles, that means I'm doing 2 times 180 degrees. So the sum of the interior angle measures, 2 times 180 is 360 degrees. Okay, I just did 2 times 180 because there were 2 triangles, and so I did 2 times the angle measures in one triangle, which is 180. Alright, let's do a 5-sided polygon, which you know is called a pentagon. So I'm going to draw a pentagon here. I'm going to pick a vertex, and I'm going to draw all the diagonals from this vertex. And in the case of this pentagon, I can actually draw 2 different diagonals from that vertex, which now I've split that pentagon into how many triangles? 1, 2, and 3 triangles. If I look at the angle measures, here's one set of 180 degrees, here's the second set of 180 degrees in the second triangle, and here's the third set of 180 degrees in the third triangle. Again, all these together would form this angle, original angle, original angle. These 2 together would form this angle, these 2 together would form that angle. We have all the angles in the pentagon, really just 3 triangles, so 3 times 180 degrees, and that's 540 degrees for the sum of the angle measures in any pentagon, any 5-sided polygon. The angle measures inside will add up to 540. And then let's look at a 6-sided. Do you remember the name for a 6-sided polygon? If you remember, that's called a hexagon. You may be starting to see a pattern here. I'm going to draw all the diagonals I can from this vertex. I could pick any vertex, really. I just want to split it into triangles, and you notice this hexagon splits into 4 triangles. So you should be thinking the sum of the interior angle measures, I'm going to have to do 4 times 180, because I've got a 180 here, a 180 here, 180 degrees there, 180 degrees here. And together that would be all of the angles in the hexagon when I kind of added everything together. And eventually, let's see, what is 4 times 180? Because I have 4 triangles at 180 degrees each, that is 720 degrees. And that'll be what the angles in any hexagon add up to. Again, you're probably getting the idea here. A 7-sided, do you remember what that's called? It's a heptagon. 7-sided polygon. 1, 2, 3, 4, 5, 6, 7. Well, a little bit of a bad sketch there. I pick a vertex, I draw every diagonal I can. Looks like I can draw 4 diagonals, but that means there are a total of 5 triangles here. And of course, it'd be 180 degrees for each of these triangles, so really I'm going to do 5 times 180, which gives me a total for all of those angles of 900 degrees. The angles in a heptagon will always add up to 900 degrees. And finally, what is an 8-sided polygon called? That's an octagon. Can you tell me how many triangles I'm going to form in that octagon if I drew all the diagonals? You notice the pattern here, it should be 6. And then I would just have to do 6 times 180 because it'll be 6 triangles, each at 180 degrees. So I'm getting 1080. 1080 degrees there for the angles in a octagon. Now, obviously I could keep going on this chart, but I don't think I need to. After you get to, if you get more than 8 sides, I know we have a nonagon for 9, a 10 is called a decagon, 12 is called a dodecagon, but after that, you just say the polygon is an n-gon. And the number of sides, actually I should just have n here for number of sides, sorry about that. It's called an n-gon, it has n sides. Well, how many triangles is an n-gon going to have? Remember, n could be anything. Well, what's the relationship here? 3 sides was just 1 triangle, it is a triangle. 4 sides had 2 triangles, 5 had 3, 6 had 4. How am I going from n to the number of triangles? If you notice, every time I'm just subtracting 2. So the number of triangles in any polygon will be the number of sides, n, minus 2, take away 2. And then, what am I doing to get the interior angle measures? Well, I'm saying there's n minus 2 triangles. There was 1 triangle, 2 triangles, 3 triangles, 4 triangles. And I was always taking the number of triangles times 180, because that's how many degrees are in a triangle. So in general, any polygon, you do n minus 2 and you times by 180, because this here gives you the number of triangles, and each triangle has 180 degrees in it. So n minus 2 times 180 would give you the sum of the interior angles in any polygon you want. Let's summarize here. This is actually called polygon interior angles theorem. And I could have just started with this, but then you'd have to believe me, and I want you to know where this is coming from. That the sum or the total of the measures of the interior angles of any convex n-gon, saying convex because this doesn't work for concave. This would be like a concave polygon, caving in there. It does not work for those situations, but that's rare. But the sum of the measures of the interior angles, remember you find the number of triangles, and that's the same as the number of sides minus 2. And then you multiply by 180 because each triangle has 180 degrees in it. So n minus 2 times 180 is a formula for finding the sum of the interior angles of any polygon. Remember that n minus 2 is the number of triangles. Keep in mind, just a quick recap, remember that a regular polygon has all congruent angles and sides. All the angles are congruent, all the sides are congruent in a regular polygon. So if I know this is what the interior angles add up to in any polygon, if I know that the polygon I'm dealing with is regular, and I want the measure of each interior angle, I mean, if you think of a regular polygon, I guess I'll have to select my shape here. Okay, let's say I have a regular hexagon. Now you know that each of these angles is congruent. They're all identical. They all have to be the same. Well, think back to when we talked about equilateral, equiangular triangles. We just took 180 divided by 3 because we had 3 angles in an equiangular, equilateral triangle. Well, in this case, I'd have to do the total and divide by 6. Because if it has 6 sides, it also has 6 angles. The number of sides and angles are the same. Well, I know that the angles are going to total up to this formula, right? N minus 2 times 180. That'll give me the total for all of the interior angles. For a hexagon, I'm dividing by 6 to find each of them. For an octagon, I would have to divide by 8, right? Because there'd be 8 angles just like there's 8 sides. Well, in general, you take the total and you divide by the number of sides, because that's the same as the number of angles, which is n. So this formula here, all I'm doing is taking the total divided by n. That would give me each interior angle. If I knew that it was a regular polygon, then I could find each interior angle in that regular polygon using this formula here. Take the total, divide by how many angles there are. Let's use this to solve a problem. You have a coin from a foreign country. It is a regular 11-gon, as you see here. If it's regular, remember all the angles are congruent and the sides are congruent. And the first thing, what is the sum of the interior angles? So what's the total when you add up all the interior angles? Well, it's an 11-gon. I know my formula. I'm supposed to do the number of sides minus 2. That'll give me how many triangles there would be in that 11gon. And then I multiply by 180 because that's the measure of each of those triangles. So in this case, the number of sides was 11, so I'm really doing 11 minus 2 times 180. 11 minus 2 just being 9. So go to the calculator, do 9 times 180. The total of the angle measures in an 11gon is 1,620 degrees, I'm finding. Okay? And then the second part is what's the measure of each interior angle, not the total, not what they add up to, but what's each one. And I know that this is an okay thing to do because it was regular. That means all of these angles are congruent. Now really, I'm doing the 1620. Don't I already know the total angle measures are 1620? And I would divide by how many angles there are, which is 11. Keep in mind what I really did here is I already did n minus 2 times 180. I got 1620, and I'm dividing by the number of sides, the number of angles, which is 11. And if I take 1620 divided by 11, it's not a nice angle measure, but that's okay. 147.27, actually the 2 and 7 repeat. And that'll be the number of degrees in each interior angle of a regular 11gon. So using our formulas there for interior angles of a polygon. Let's do another example here. I want to find in this, what kind of polygon we got? We got 1, 2, 3, 4, 5 sides, 5 angles. This is a pentagon. I want to find the measure of angle S. I'm noticing that S and T are congruent angles. Okay. First thing I should do is find the total. What do all the angles add up to in a pentagon when there's 5 sides? Remember the formula. You do number of sides minus 2. So 5 is the number of sides. It's a pentagon minus 2 times 180. Because if I drew those diagonals, I would have 3 triangles. That's why we're doing 5 minus 2 times the number of degrees in each of those triangles. I do 3 times 180. And actually we had this in our chart from earlier. The angles in this pentagon should add up to 540 degrees. I like to put it in the middle because then that helps me remember that that is my total. That's what I'm adding up to. But I gotta find what's left for these 2 angles, so I'm going to go ahead and subtract the angles I already have. Angles I already have given in the picture. So I'm going to do 540, I'm going to subtract 93, I'm going to subtract 156, I'm going to subtract 85, I'm just doing this on the calculator. And I have 206 degrees left, but that's for 2 angles that are congruent. So I'm going to divide this by the 2 angles since they are the same. And I have 103 degrees left for angle S and T, so that all these angles add up to that 540 that a pentagon should add up to. So again, our interior angle measures there. Alright, these next 2 examples are using the formulas and working backwards to try to find the number of sides a polygon had. In this case, how many sides does a polygon have if the sum, or the total, of its interior angles is 1,440? I don't know the number of sides of this polygon, but I know that the total, or the sum of its interior angles, is 1440. So think about this. I need the formula. I need to know what formula would give me the sum of the interior angles. What formula would give me 1440? I know to find the sum of the interior angles, you do the number of sides minus 2 times 180. And right now I know the answer to this. It's 1440 is the total. When I did the number of triangles, right, n minus 2 times 180, I got 1440. Solve for n. And actually, there are 2 ways you can solve for the variable n here. One way to do it would be just divide by 180 right away. And then you would have n minus 2 equals, and if I do 1440 divided by 180, I get 8, and then I could add 2 to both sides, and 8 plus 2 would give me number of sides is 10. And it must be 10 sides then. I guess I could write sides here. The other way to solve, you could distribute and get, I just want to show both ways so you can decide what you like better. You could get 180n minus 360 equals that 1440. I just distributed 180 to n and negative 2. Then I could add 360 to both sides, and 1440 plus 360 would be, 1800. And I could divide by 180, and either way you get n equals 10 sides. So I guess either method you can use to solve, but you do have to use this setup of the formula to figure out where to go to find those number of sides. So using the formula working backward to find sides, and this one's even trickier. This time you have to find the number of sides of a regular polygon. Notice the keyword is regular, meaning all the angles are congruent, all the sides, whose interior angles each measure 144 degrees. Find the number of sides of this regular polygon if each interior angle measures 144 degrees. So right now I need the formula that would have let me find this, the formula that would yield 144. This is each interior angle measure in a regular polygon. Well, each interior angle measure, that means first I would need the total of the interior angles, which is the n minus 2 times 180. But if this is a regular polygon, and I'm looking for each interior angle, I would divide this by n, the number of sides, the number of angles, and that would yield each interior angle, which here is 144 degrees. Okay, so this would have been the formula, to find the measure of each interior angle measure of a regular polygon. This now equals 144, and I got to solve for n. And if you remember back to trig, we're dividing by n, and I don't like having that variable in the denominator there, plus there's two variables, so undo divide by n, get it out of the denominator by multiplying by n on both sides. And now I have n minus 2 times 180 equals, on this side I have 144n. And since there's an n on both sides, I'm going to have to distribute on this side. So I get 180n, and then it would be minus 360 equals 144n. And then I would subtract the 180n because I'm noticing there's a variable on both sides. This is the only number, so I'm going to keep the negative 360 on this side. I'm going to do 144n minus, I'm subtracting the 180n to cancel it away from there. And I get negative 36n. And it's fine that it's negative because I'm going to divide by negative 36, and this will turn positive on this side. And actually it turns out that n is 10 sides, just like before. Oh, but that makes sense, right? Because 10 sides, the sum of the angles was 1440, and 1440 divided by the 10 angles there are, each one would be 144. Okay, so this is an example of using the formulas when you already know the sum of the interior angles, or you already know each angle measure in a regular polygon, to work backwards and find the number of sides. And more to do today. We talked about interior angles. Well, we're also going to talk about exterior angles. And remember that an exterior angle are the angles outside of a polygon when you extend a side. So like when you draw the line out further from a side, all of these would be called exterior angles. So we're trying to figure out what's the sum or the total of those. And to do that, I'm going to show you something in Geometry Sketchpad. So I have this regular polygon, and I extended all the sides out in the same direction. And I'm going to grab this vertex. Now if I bring these angles together, something cool will happen. Remember, I'm still looking for what do all of these exteriors add up to. Eventually, if I can bring this all the way, this polygon becomes basically a point. And if you notice that these are all my exterior angles, and together they form a full circle. So it's kind of neat. You just bring all the vertices together to a single point, and the exterior angles make a full circle. What's the angle measure of a full circle? 360, right? 360 degrees is a full circle. So the exterior angles actually add up to 360 degrees. It doesn't matter how many sides you would have, because you're always going to just grab that shape, make it smaller to a point, and suddenly the exteriors make a full circle. So this one's neat. No real formula, it just is a number. Okay, exterior angles always add up to 360 no matter what. So I'm going to fill that in our formal theorem, polygon exterior angles theorem. The sum or the total of the measures of the exterior angles of a convex polygon is 360 degrees no matter what. And then, just like before, we're also going to focus on regular polygons. Well, if it's a regular polygon, all the angles were congruent. All the interior angles were congruent, but that means exterior angles are also congruent, and we're going to have the same number of exterior angles as interior angles as the number of sides. So to find each exterior angle of a regular polygon, I'm just going to take the total 360, and divide by how many there are. What variable gives me how many angles there are? Well, it's the same as the number of sides, so n. So this would be the formula to use if you want each exterior angle. Just do 360 divided by how many there are, if it's a regular polygon. And let's do some examples here. So find the measure of angle x. 32 degrees, exterior angle. 2x minus 12, an exterior angle. 2x, exterior, x is an exterior. Well, this would be 90, right? Because this is 90, and these two add up to 180. Oh, that's another thing to talk about. Every exterior and interior add up to 180, right? Exterior, interior, linear pair add up to 180. Exterior, interior add up to 180 because they're a linear pair in a line. It's a little point there, but now that we know, what do all of the exterior angles of a polygon add up to? 360 degrees, because I could bring that to a point. It would be a full circle. So I'm literally going to add up everything. Set it equal to 360. So if I take the first one, 2x minus 12, and I add 32, and I add 2x, and I add x, and I add 90, that should be the last one, all of these together should equal 360 degrees. Let's combine like terms here. 2x, 2x, and x. We got a total of 5x. Negative 12, positive 32, we're at 20, plus 90, so plus 110, equals 360. Get x alone, subtract 110, and we have 250 on this side, then divide by 5, and x equals 50. If I plug that back in, it should all work out here. 50 degrees, this would be 2 times 50 or 100. 150 plus 90, 240, 272. This would be 2 times 50, 100 minus 12, 88 plus 272. Yep, looks good. Okay, it adds up 360. Okay, what about in this next one? What would the measure of x be? Hey, x is an exterior angle, right? And it's the exterior angle of a six-sided figure. What's a six-sided figure called? A hexagon. What do you notice about this hexagon? Well, all the sides are congruent and all the angles are congruent, so it's a regular hexagon. So therefore, all of the exterior angles would have been the same as well. And if it's a hexagon, let's see here. The exterior angles should all add up to what? They should add up to 360. So if I divide that by how many exteriors there would be if they were all drawn, there'd be 6 exteriors just like there's 6 interiors because there's 6 sides. And it looks like x measures 60 degrees. Okay, so working with exterior angles here. And we also want to be able to use those formulas and work backwards. So here, if you know that each exterior angle of a regular polygon is 72 degrees, how many sides does it have? Okay, I don't know how many sides it has, but I know each exterior of a regular polygon is 72. Well, then what formula would have given me 72? Like, how would you actually find each exterior angle of a regular polygon? Well, I know all the exterior angles add up to 360, don't they? And if I'm looking for each exterior of a regular polygon, then all the exteriors would be the same, and we know that formula is just 360 divided by how many exteriors there are, which is the same as how many sides. Right now, I know that the exterior angles each measure 72 degrees. I'm just solving for n. I don't like that n's on the bottom or in the denominator, so first you multiply by n to bring it over here, and you have 360 equals 72n. All you got to do now, 360 divided by 72. And I get that the number of sides is 5. And you have to get a nice whole number for number of sides. That makes sense. So in a pentagon, right, that's 5 sides, each exterior angle measures 72 degrees. And another example here. In this example, I'm saying find the measure of an interior angle and the measure of an exterior angle of a regular octagon. Notice it is a regular octagon, so all these sides and angles are congruent. Well, how do you find the measure of an interior angle? Okay, think back to the beginning. The interior angles add up to n minus 2 times 180. Remember that n minus 2 was the number of triangles. That's why we multiply each triangle by the angle measures of a triangle 180, or the total of the angle measures. But if it's a regular octagon and you're finding the measure of like one and interior angle, you're going to divide this by how many interiors there are. It's an octagon, which has 8 sides. Remember, in general, you divide by n. In this case, I'm going to fill in my number of sides, which was 8. So I'm doing n minus 2 times 180 is 8 minus 2 times 180 divided by n, and the number of sides was 8 here. So really I'm doing 6 times 180, right? 8 minus 2, so it would be 6 triangles times 180, and each of those triangles divided by 8. Let's see what I get here. I'm doing 6 times 180 divided by 8, and I get 135 degrees. This is the measure of each interior angle of a regular octagon. And then how do you find the measure of an exterior angle? That's right up here. We know the exteriors add up to 360. And how many exteriors are there? Well, it's the same as the number of sides. In this case, I know the number of sides is 8. So I'm doing 360 dividing by the 8 exterior angles that I have. And 360 divided by 8 is 45 degrees. So that would be the measure of an exterior angle. And then kind of a way to check if you've done this right. I'm going to bring up an octagon actually. 8 sides here. Oh, that's a little small. We'll fix that. So an octagon, 8 sides. I've got an interior of 135. I've got an exterior of 45. Now, an exterior would be if I extend one of the sides. I have a 45 degree angle here, 135 degree angle here. We mentioned this before. What should the measures of an interior and exterior always add up to? They should add up to 180, and 135 and 45 do. And that's good because each of these is a linear pair. They add to 180, check. So today, working with angle measures in polygons, looking at interior angle measures and exterior angle measures, and then finding each of those angle measures when it's a regular polygon as well.